Hey robot makers, hope you're having a good day so far. So if you want to learn how to make your own Raspberry Pi Pico powered drone powered by MicroPython, then this is the show for you. Let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, let's get over to the slides today and we can crack straight on. So that's a bit of a sneaky peek of what we'll be building. That's not going to be the finished 3D printed body, but we'll get into all the details of it right away. So we're going to be making a couple of videos on this topic because there's too much to unpack in a single hour. We'll go through what parts we need for this project. This is kind of a starter list that may well change as we evolve the project. We'll start creating some of the code for the sensors. We'll have a look at that as well today. We're looking at powering the drone, the kind of choices that we have to provide some power to the motors and to the sensors and the flight computer. We'll be doing a test flight at some point in the future. Very, very much looking forward to that. We'll be doing one inside first of all, maybe strapped to some kind of harness so that we can test does it cope with being moved around by the wind, and will it actually provide enough thrust to lift the model off the ground. But looking at the 3D model itself, like I said, we've this first iteration that I've created is just very basic. It's just to hold the parts together. We will evolve the shape of that as we go on. The idea is this is quite a flat piece and can be very quickly 3D printed and iterated on. And then the goal of this project will be to create a custom PCB that we can share, an open source hardware PCB, and we'll be able to put all the components on there and have like a really rigid drone that we can very easily put together as a little kit. Okay, does that sound cool? So here are some of the parts we'll need for this project. So we're going to need a Raspberry Pi Pico. I'm using the 2W version. This is because the Pico 2 is a lot more faster, and therefore the number of calculations it can do per second is obviously a lot greater than the original Pico. We're going for the W version because that has Bluetooth on board. More about that in a little bit. We'll be using a GPS. I've got a whole bunch of different GPS modules here. I'm just testing to see which one I think works the best so far. I actually picked this one up at Liverpool Makefest a couple of years ago. I think it was only about £5 to buy, but when I plugged it in, it just got really, really hot and didn't work. So I ordered a bunch of other ones. Here's another one. They all seem to be based on this same Neo chip. If I just sort of hold this, you might be able to see the little chip there. U-blocks. So they're all based around this kind of, is it Neo 6 chip? They all speak the same language, and they also have these little ceramic aerials. So they're interesting. They have different shapes of these. This one's kind of like a long one. This is more of a rectangular, square one. I've got a rectangular one as well. So yes, these are quite small, but they can add a lot of extra information to our drone. We'll get into the details of that a little bit later on. Next up, we need some IMUs and Inertial Measurement Units. I've got a whole bunch of these. So I've been playing not so successfully with this. This one is called the GY91. We'll get into the details of that and what that can do. But essentially, this can figure out where the robot is, where the drone is in 3D space. So is it tilting? Is it moving forwards? Is it falling? All that kind of stuff. And then we can send that information to our flight computer and adjust the motors accordingly. So an IMU is like one of the key parts of our drone. Next up is the battery. So I've purchased this battery, but this looks like it's a slightly different wiring than this little module that I've got for these Pimroni ones. So it's actually like wired back to front. So if I put this in here, it'll just explode. I don't want that to happen, but these are quite similar. This one I bought is a 500 mAh, so it's very, very lightweight, rechargeable, LiPo. It's also very thin, so we'll be able to strap onto our drone quite easily. And it's also removable with this little connector, and it means that we can charge it up. I've also got these other ones. These are the Galleon ones from Pimroni. I love these little batteries. They come in a hard case. Put that the right way up. And yeah, these are 400 mAh, so a little bit less. But they also have these little LiPo Amigo Pros, which is another one of the parts. And that enables us to both power the robot, the drone, and also charge it up just by putting in some power. USB-C, so we can actually have this as part of our drone. Next up, we need some electronic speed controls for the servos, for the motors, for the propellers, and I've gone with these little DRV A833 chips. You'll need two of these. These can do motors each, and we're going for a quadcopter design, so we'll need to have 4 propellers, 4 motors that we can actually control. Next up is the actual propellers and motors themselves. So I went with a little kit, basically the cheapest one that was available on Amazon, and it comes with pairs of clockwise and anti-clockwise propellers. We'll get into that, I think, in a later video, and exactly how to pair these up. These might not even be in the right orientation, but we'll have a look at what that's all about. But these are very, very small. You can see there, basically just the size of my thumb, really. And these are not particularly connected up or anything like that at the moment, just there for illustration. And we'll need some kind of 3D printed chassis, so I've gone with the kind of, I call this the dead cat. There's some YouTuber that's cat had died, and he had it taxidermed, he had it stuffed into a drone so they could actually fly his dead cat around. But yeah, this kind of orientation where you've got all the electronics and things in the middle, and each of the arms has just got one of the propellers on. That's the kind of design I'm going with. The reason I've got 2 of these is this one, the motors wouldn't fit in because the tolerances weren't quite right, and the new one I've got, they're a bit too loose, so I'll have to iterate over that a few times to get it just right. And then yes, the last part that we had on there was this LiPo Amigo Pro, which is this little component here. It's got a little sticky dot on the back there obscuring the name, but it's essentially just a LiPo charger. So we could either include this on the drone, or we can have this as an external thing. We'll have a look at that. So Ford's asking, why would you taxidermy his dead cat? Meow. Meow. I don't know, he just decided to do that. I think there's videos on social media that you can look at if you're interested in that. Right, let's go for, there we go, sorry, next slide. So how are we going to control this drone? You've probably noticed there's no first person camera or anything like that. We might well put a camera on this project later on so that we can wear some kind of like goggles. Got something in my eye there, and we can see what the drone can see. That'd be pretty cool. But to begin with, how are we going to control this? Well, I thought a really easy way, a reliable way, is Bluetooth. Now, that might not be fast enough, as it turns out, to issue commands to make the drone move around, but all the flight computer, what the flight computer will do is make sure that the drone is always stable, so it's not relying on our controller to actually make sure that it's flying properly. Simply we'll issue commands like go up, go down, left, right, go faster, go slower, that kind of thing. So that's what we can use our gamepad for. So you can get these PCBs on kesrobots.com as well if you're interested. But yeah, for now we're just going to use Bluetooth. That also means that the range that we're going to be flying with this drone is within the Bluetooth range, which isn't very far. But just to keep things simple, this is what we're going to stick with for now. We may well change that in future iterations of this drone. So what do all these things actually do? So we talked about the Raspberry Pi Pico 2W. That's going to be our flight computer. It's going to manage all the inputs, control the propellers, control the motors. The Inertial Measurement Unit, this GY91, we'll talk about why I picked that one, and we'll also talk about if that's the best option that there is out there. There's lots of different inertial measurement units, but essentially it's a digital compass, got a barometer to measure air pressure, which can also measure, it can estimate altitude. We've got the battery, which is going to provide the power to all the different parts, the motors and the sensors, and also the flight computer. The electronic speed control units, the DRV8833s, they're really, really cheap to buy, really small, very lightweight. We only need 2 of those. The props and motors themselves, you can tend to buy those in kits. I may well iterate through a few different versions of that as well later on, but that's what we're going to use those for. And then the 3D printed chassis is going to provide the base for all the parts to stick to. And of course we need some kind of battery to power all this as well. I've gone with a very small battery to begin with. That's going to limit the amount of time that this can fly for, but it also means that it's very lightweight, and therefore there's a balance to be had between weight and power. Cool. So let's have a look a bit more detail about the flight computer then. So yes, going with the Raspberry Pi Pico 2W. That's going to take all the readings from the sensors, going to calculate our current position. We'll talk about position in a minute or two. It's going to process all the input commands from the remote control. It's going to update the motors to maintain the desired position, and it's going to report back any readings for debugging as well. So the acceleration, gyroscopic motion, so is it actually turning and moving, a digital compass so it knows which way it's heading, barometric pressure for altitude, and we can also have the yaw, pitch and roll provided back as some data as well. We can also look at those remote control commands that are being sent to the drone, and therefore it can say yes, I've received a go up command, for example. The GUI91, this is the IMU, the Inertial Measurement Unit. This is going to provide position, movement, rotation data. Also going to provide this barometric pressure for rough altitude and height data. It's going to be used by the flight computer to calculate this roll, pitch and yaw, and we'll talk about that in a little bit more detail as well. The battery, so like I said, I'm not sure I'm going to use the actual battery. That's one I've ordered. When I come to actually power that in, I noticed that the positive and negative are actually inverted for the module that I'm using to both charge it and to power the electronics. The the LiPo Amigo Pro from Pimroni. It's very lightweight, has about 15-20 minutes of flight time estimates. We can confirm that once we've actually got the drone flying around. And it's very easy to swap this battery in and out because it's got that little plug on it, and it's also going to be very affordable. So there's a question there, where is the parts lists? So I will put that together and write it up next week. I've not got around to that yet. And like I said, this is really early days. There's a lot for me to learn in this project. So I'm kind of learning as I go on this one. I've not built a drone before, but I thought, flying robot, it's time that we did this. So yeah, there's a lot of learning, a lot of failure to be had for me first. So the DRV 8833s, these are these little chips, very, very small. They've got a bunch of pins on there, you can see on the back there. So these ones, also known as electronic speed controllers, these ones can be used to control servos with pulse width modulation, but they can also power motors and control the speed and direction of the motors as well. So each of these can control 2 motors. We need to have 4 of them in total, so we need 2 DRV 8833s. I also looked at another version, which is these MX, the 1508, I think they're called. These are a little bit chunkier, do the exact same thing as the DRV 8833s, but these are a little bit bulkier, so I thought we'd go with the smaller ones. I think the other ones are a bit more powerful as well. So the motors and props, this is a little kit that I bought from Amazon. It was very, very cheap. So 2 pairs of clockwise and 2 pairs of anti-clockwise propellers. You can see the black and red, that just denotes the sort of orientation of the way that the propeller spins. You want them to spin in opposite directions to create some lift. And yeah, there's 4 of them, and there's 4 motors as well. They're going to be connected to the electronic speed controllers, and that's going to be the thing that powers and defines how fast the motors are going to be spinning. And the 3D printed chassis. So like I said, I've got a very, very early prototype of this. At the moment you can see there we've got some holes for mounting the Pico on. We'll have a look at that in a second. The overhead, I'll just show you here. These are all likely to fall out if I tip this too far. You can see there we've got the propellers, we've got the Pico mounted there. It's literally just sat on there at the moment. I've not screwed it in. And other electronics will be above and below that as well. So we'll iterate on that one later on. And we've got this LiPo Amigo Pro, which is the charger. It provides power to the battery when it's charging. This will also provide power to the Pico, to the sensors and to the motors, to the motor drivers, the ESCs. And it uplifts the battery from whatever it is, 3.7 volts to 5 volts. So when I did a drone course, I actually went on a drone course a couple of years ago to get like that's not a license to fly drones, you don't actually need them, but just to get a certification, so I understood a little bit more about flight and what goes into drones. We were looking to see, what does a full battery look like, a full LiPo, and they tend to be 4.2 volts, and they will go down to 3.2 volts at the very sort of lowest end. So this little circuit will actually bring the voltage up to 5 volts, which is quite clever. It's like a buck converter, and that means we've got enough power if we need 5 volts for any of the circuitry. The GPS units, for example, typically require 5 volts. I think everything else requires 3 volts, but the motors, for example, probably work better at 5 volts as well. Also has a nice little power on and off button. I don't know if you can see the LED. If I power this on, there's a little LED light that just lights up just where my finger is there. So that's just taking power from this little gallium battery that's plugged in there. So we can have another device connected to that, which is all the electronics, and there's also some pinheads, some pin-out headers there. We can also connect things up to. So positioning, the science of where. So let's talk about relative versus absolute positioning. So relative positioning can be calculated by measuring angular velocity and compass headings. Absolute position can be calculated measuring the distance of, let's say, at least 3 satellites in orbit. So you can triangulate your position on Earth, and at least 3 different, or at least 3 different Bluetooth beacons that are at known fixed locations, and triangulate from those as well. With the satellites, there's lots of different satellite systems out there, and you can actually debug the GPS modules that you have and see which kind of satellite systems you're actually using. So there's many different ones. There's like European ones, Russian ones, American ones, and so on. So we can actually use a combination of relative and absolute positioning to make our drone know where it is in 3D space. So relative position can be measured on board without the need for any external devices. The issue with relative positioning is it tends to drift. So you don't truly know where you are, you just have a good estimate as to where you are. Absolute positioning requires fixed points to be detected, but this usually requires additional devices such as a GPS satellite or Bluetooth beacons. Relative positioning is very, very cheap. So these modules are typically, under $10. They're very, very cheap. Absolute positioning with these GPS units, these are under $20 typically. They have these little antennas that are detachable as well, but they tend to use the same kind of chip, which means that our code is easy to migrate to different ones if we change our mind later on. So the positioning sensor modules for relative positioning, so there's a whole bunch of these. I've got quite a few of these on my desk that we'll have a look at in a minute. So there's the MPU 6050, that's a gyroscope and accelerometer. Also has a temperature sensor on board. Temperature does change how these gyroscopes and accelerometers work, so we can factor that temperature in when we're calculating our relative position. There's this GY271, it's also known as those other numbers there, which is a magnetometer, so that can detect in 3 different orientations magnetic strength, and we can use it as not very crude, but we can use it as a digital compass, so we can figure out which way magnetic north is from where we are, and therefore we can use that to work at our position. There's the MPU 9250, so that combines the gyroscope, accelerometer and magnetometer from those 2 units above, and I think I have one of those just here, which is this one. It's like quite a long looking one just there. I think it says along the bottom there that it's the 9250. 9250/6050. So we'll get into some of the complexities of using these a little bit later on, but we'll have a play with some code to actually see if we can actually get these to give us some readings. So here's a comparison of some of these modules. So the 6050 on the left hand side there, that's got 6 axes or 6 degrees of freedom, and it's essentially an accelerometer with XYZ and a gyroscope with XYZ. That gives us our 6 axes. Uses the I2C interface, doesn't have a magnetometer on there, doesn't have a pressure sensor. And the pressure sensor we can use to estimate our altitude or changes in our altitude. It runs on 3.3 to 5 volts, and it's between $2 and $5, pretty cheap, and they're pretty easy to use. The next one then, the 9250/6500, that's a 9-axis, so we've got the accelerometer XYZ, gyro XYZ, and magnetometer XYZ. So again, that uses the I2C or SPI interfaces, whichever you prefer. Does have that magnetometer on board, so we can have that digital compass. Costs a little bit more than the previous model, and because it's got that extra complexity of the magnetometer, the ease of use is a little bit less than the previous one. The one I put it as the go-to one for now, I might change my mind after this, after wrangling with the code for a while, combines the 9250 with the I think that's probably a BME 280, which is like this one here. So Pimoroni sell these little breakout boards. This one has got the BME 280, which is that little silver chip in the middle there. And if I spin this round, you can see on the back there that this actually says on it pressure, temperature and humidity. But it's really just the pressure that we're interested in that particular module. So that's 10 axes or 10 degrees of freedom. So we've got the accelerometer XYZ, gyroscope XYZ, magnetometer XYZ, and we've also got that air pressure for our altitude. So there's a lot of sensor data coming from that one sensor, and I think that sensor can actually do 1,000 readings per second. It has one kilohertz refresh frequency, which is just insane, the amount of data it can squirt out to your flight computer. Then we've got some other ones. There's the BNO 055, that's another 9-axis one, accelerometer, gyroscope and magnetometer. Doesn't have the air pressure sensor on there. Kind of a higher price than the previous one, that's why I've not chosen that one. And then there's that LSM9 DS1, which again has the 9-axis accelerometer, gyroscope, magnetometer, no pressure sensor on there as well. So it's not one of the easiest ones to use, this one in the middle, and we'll look at why that is when we have a bit of a demo in a second. So gyroscopes and accelerometers, so the way that they work is actually quite magical. They are a mechanical device, so they have a moving part within the silicon, which is crazy. So they are micro-electrical or electromechanical. They have these little fins that move, and the distances between them can be measured as like a capacitive, like a capacitor in effect. So you can measure the capacitance changes, and therefore how quickly that changes over time will give you things like the acceleration. The gyroscope, it can detect the orientation, so what's the distance between these little fins. Very, very clever. So they're using drones in self-balancing robots. Typically use the I2C protocol, clock and data, so it just requires 2 pins plus the voltage and ground. And this MEMS works by measuring gravity and force applied to the digital gyro. The accelerator takes into account the orientation of the device, and we can fuse these together in some clever fusion algorithm. We'll have a look at that as well in a minute. And includes a temperature sensor, because again this can be used by this digital measurement processor to adjust the calculations. So the higher up you go, the colder it'll get, and therefore you just need to adjust things because things can shrink down, and we need to take account of that. So it returns 7 values: the accelerometer XYZ, temperature, and gyro X, Y, and Z as well. The GY271 and the other numbers you can see on there, that's also MEMS, measures the Earth's magnetic field. So it is very susceptible to other magnetic fields around where you are. So typically what you will do when you're using these is you'll let it sit for a minute or two, a couple of seconds, and you'll take lots of readings, and you'll find that one of the axes is much stronger than the rest, and that's the one that's pointing towards true north. And if it's not sat, absolutely pointing at that, it'll be a combination of all 3 axes. So you'll be able to figure out which way is north. But we need to know where we roughly are on the Earth because of something called declination, and we'll have a look at what declination is on this next slide. So declination is the Earth's magnetic field, and where you are on the Earth, which hemisphere, and where you are kind of your longitude position on there, that can affect the direction that you're pointing in. So we need to roughly know what our declination is to be able to use the magnetometer correctly, and it's typically a figure that you'll put into the calculation when you're doing that. So you just have to assume that you are in London or in New York or whatever the latitude is on there as well. So why do we need this Madgwick? What is it? What even is Madgwick? So he's I've got some notes on here I was just going to pull up. So Sebastian Madgwick is a British Google engineer, and he came up with this really clever, computationally efficient, it's called a gradient descent based algorithm, and it's basically to stabilize sensor data. So it can take in lots of different sensor data and correct where it thinks your position currently is. So it will take in the strengths and weaknesses of each sensor and use them accordingly. So a gyroscope is really good short term but drifts over time. So because gyroscopes, if you think like a traditional gyroscope where you're spinning something, and if you sort of tilt it, you can feel the force. Sounds like something from Star Wars. You can feel the force being applied because of the gyroscopic motion. Gyroscopes are really good for figuring out which way you're rotating. The accelerometer can tell which way up and down is, but shakes a lot, so it's very, very noisy from a shaking perspective because things are always moving around. And the magnetometer tells you what direction, but it can be confused by nearby magnets. So we have to take lots of readings over time to kind of smooth out, to filter out any noise. So Madgwick, which is named after Sebastian Madgwick, mixes all these sensor data together to get the best guess of how to know where the device is moving and turning and so on. So how does it work? It starts by making a guess. It says, I think you're facing this way. That's the orientation. It then listens to the gyroscope. It watches the gyroscope to see if the device is spinning, updates its guess based on that. Then it checks to see gravity and compass. So it uses the accelerometer and the magnetometer to check if the guess is wrong. It then fixes the guess. So if it doesn't match the gravity or compass, then it gently corrects it. So that's over time. We're going to add little amounts of change so that we're not sort of chopping around. And it repeats that over and over and over. So happens many times a second and keeps the guess accurate over time. So very, very clever algorithm. There's quite a few other ones as well. But yes, I regret putting this slide together now. I spent all afternoon fighting with the magnetometer. We'll have a look at that in a second. So the GUI91 is another MEMS device. It measures 10 degrees of freedom. So we've got that 3-axis accelerometer, 3-axis magnetometer, 3-axis digital compass, and we've also got that barometric pressure for the altitude estimation. I think there's even a temperature sensor in there as well. So there's an awful lot going on that one board. So if you like these videos, you want me to make more of these kind of videos, if you definitely want me to make more of these drone videos, then definitely drop me a comment below just saying, yes, more drones, please, Kevin. If you've not given this video a like, please give this video a like. It means so much to me when people do that. And if you've not subscribed to the channel, please subscribe. It means so much to me when people subscribe to the channel. So yes, it's just for me and my satisfaction. And I do go live every single Sunday, 7 o'clock British summertime. So I think, yeah, we're a couple of months off yet, that changing back to GMT. So British summertime is where we're at currently. Okay, let's have a bit of a demo then, shall we? Let me go back to me for a second while I get my screen sorted. And we can just move that around there. And what I'm going to do, I'm going to show you on this overhead camera. Right, so I've got this little breadboard here, and I've got a number of different circuits. This is actually a GPS. It's a tiny little GPS. I've just blue tacked it to my desk so it stays the right way up, because these have to be facing upwards. And that solid light on there tells me that it hasn't actually found any satellites yet. It should be flashing when it's found some satellites. There's a tiny little battery on there as well, which is quite cool. I've got a Raspberry Pi Pico. I've got a whole bunch of different IMUs on here, but this purple one, this is the GY91. If I can get that to go in focus, do I have to have it right in the middle of the screen, I think, for that. As you can see there, it's got a bunch of header pins on it, and if I get that the right orientation for you, of course I have to get that wrong. So we've got voltage in 3 volts ground. We've got the system clock, system data, which is the I2C, and then there's a bunch of other ones which we don't really need to worry about. There's also 2 great big mounting holes on there as well. So you can see that it's a pretty complicated little board. That's the one that we've actually got plugged in there. I've also got the GPS plugged in as well, just to sort of show you that. And you can see we've also got, there's the prototype that we've started to put together. Put some holes on there so we can mount things kind of up. But we need to be mindful of the kind of balancing. We don't have things kind of lopsided so that one motor is working more than another. So there's a whole bunch of things to consider there. I'm way out of my depth on this particular project, but this is why it's fun. Okay, let me get over to Thonny. And what am I going to run first? I'm going to run this one. Let me just grab this over here. Right, so if I grab, why can't we see that on the screen? Let me just figure out what's going on there. That should show me both the screens at the same time, and it's not doing, which is a bit frustrating. So let me just edit that. So that needs to be for that current application. Let's make that a secondary display. It is primary display. Well, that's weird. I'm not sure why it's not showing Thonny up there. Let's just go to this view, and there we are. Okay. So this first demo program I've got is basically going to talk to this GY91, and it's going to read out some numbers, and then we're going to plot these on this little plotter over here. But first of all, let's just have a quick look at what this program's doing. There's an awful lot in here, so don't worry if this seems a bit complicated. I will simplify that and go through this code once I'm happy with this. So the first thing we've got is a whole bunch of registers. So we're going to set up our I2C interface. So I'm just using pin 0, pin 1, which is the first kind of ID that we can use for I2C. We then got some MPU 9250 registers. So even though this is the GY91, it contains an MPU 9250. So we've got the MPU address, we've got the power management to kind of switch it on. You can basically tell this to switch on. We have some BMP 280 registers, which are the air pressure sensor registers. There's a whole bunch of them. And then we've got this class to represent this Madgwick filter. So we're not going to use the magnetometer in this. I'll talk about that in a little minute or two once we've got this running. But that's just simply going to set up a bunch of variables in here. We've got this little, are they called quaternions? I don't know what the actual correct pronunciation of this is, but it's simply a representation of a position, like a vector. Then we've got this update. So this is going to take in some gyroscope and accelerometer, and also the air pressure, or is that temperature. We're then going to set them to be whatever the self.q is, which is this 1.0000. And then I'm going to do a whole bunch of math on this. I'm not going to go through the theory of this. There you go. That's that quaternion. How do you pronounce that? I should look that up really. So yeah, we're going to basically do a whole bunch of calculations on that, integrate them into this, and the integration is part of what the filter does, how it merges together different readings to correct the guess. We're going to get the Euler as well, or Euler. I always think that's Euler, it's Euler, isn't it? He's another mathematician. So this is going to produce the roll and the pitch. So we have three different ways of figuring out what our drone is doing. So we have pitch. So if I'm pointing, if this is kind of forwards, our pitch is if we're pointing up and down. Our roll will be kind of that orientation, and our yaw is kind of on, spinning that way round. So they're the three things that we need to know about. So yaw is kind of like the heading that you're on. So we're just going to work out roll and pitch because we haven't got that third one in from the magnetometer. So the first thing we need to do is wake it up. So we write to this address on I2C, the MPU address, the power management address, and we just send it a byte of data, just saying wake up, kind of poking it. We then check the config of this BMP 280. So we write to a memory address, and we write to another one to the config, and then we're ready to read back some data then. So reading from the sensors, we just do a read word. So the data is going to be read from the memory address, from the particular register, and then how many bytes of data, I guess that is. Then going to these kind of things, we see double arrows by 8. This is a way of bit shifting things around. So typically when we have registers, this is like really low level architecture stuff, and we're working in binary, so we want to move things around, and that's what these things are doing there. So typically, to try and keep things really efficient, to calculate and also to move data across the internal buses of these things, because they're usually quite small and slow, we try and shove in as much data as we can. So we'll make use of the registers. So if we have an 8-bit word, for example, we might say the first 4 bits are this and the next 4 bits are that. So we need to split those up. And these kinds of little bit shifting operations help us split out those two different things. They're going to read in the barometric pressure, so we have to do a whole bunch of things to do that. We also get the temperature and pressure, but we're only really interested in the pressure. And we can then convert the pressure to altitude, so there's a little calculation there, sea level, and yeah, we basically just do that little calculation there to calculate based on what the pressure is at sea level. It's interesting, on different planets, you measure the altitude from the surface of the Earth, from the surface of the planet, not the level of the liquid on the planet. I think the Earth's one of the only planets where you actually measure altitude from the sea level rather than from the surface, as it were. Then we make an instance of this Madgwick filter. Sounds like magic, doesn't it? Madgwick. We then print out for the Thony plotter the X, Y, Z for the accelerometer, the X, Y, and Z for the gyroscope, the temperature, the altitude, and the pitch and the roll. And then we basically just go around this many times in a loop. So let's run that and see what we actually get out here. So if I just move this up a little bit. Where's the there it is. So we're getting a whole bunch of readings. So if I grab hold of this, this is why I wanted to kind of show you this at the same time, but it's not allowing me to do that today for some reason. So I'm going to move this around like this. This is what I'll be doing. If I go back over to Thony, you can see those values are changing as I'm moving around with this, just by wiggling it around like that. Now normally if you use like an iPhone or something and you have some kind of let's go for like the level app. There's so much technology in an iPhone and they make it look so elegant and so simple. So if I go for the level, for example, and I move this around, it's really solid. You don't see like jittering numbers. It doesn't kind of go between two, and it's also really quick to update. That is really hard to do when you're doing this as a DIY. Right, so that's the first one I wanted to show you, and let's put this into the plotter. So if I go over here to the plotter, so you can see you've got these 4 different values over here. 3 different values. So the blue one which isn't changing is our actual altitude. I've had to divide that by 100 because it was getting kind of crazy. You couldn't actually see the other 2 axes because they were being sort of squished right down on the scale. So the blue isn't really going to change very much as I move this up and down 30 centimeters. So if I make this roll, if I roll it over to the left and then roll it over to the right, you can see that the green one seems to be changing. If I change the pitch of this, if I tilt it up, you can see the green one is going up, and if I tilt it down, you can see the green one's now going down. If I do like a pitch and roll up to the right, you can see the green and the orange one change, and if I pitch nose down to the left, you can see it change again. And just so you understand what I'm doing, I'm kind of pitching it up like that, and then kind of pitching it nose down. And they're the different readings that we're getting there. Cool. And if I just sit that on the table, you can see there it is pretty straight, pretty solid, but over time it will drift. You can see there that one seems to be sort of going a little bit higher each time, and that's part of the drift that you get with these relative sensors. So we need something that's absolute, like the magnetometer, because the North Pole is not going to change position based on where we are on the Earth. Or the GPS unit, which can grab data from satellites. So I've got a GPS unit plugged in, and I think it'd be quite cool to have a look at this as well. So I think this is the GPS debug. Let's just try this first of all, and we can actually get rid of the plotter window as well. So let's do that. So let's get rid of plotter. Right, so we're getting a whole bunch of things on the screen. So what on earth are these? So we're reading from our GPS unit serial data. So it's spitting out there these GP, GSW, GSA, VTG. They're all different satellite systems that are out there. We just need 3 satellites from any of the different systems to be able to triangulate our position. So we can see that we're actually receiving satellite data, we just haven't got a strong enough one. All these commas on here are missing bits of data. So I'm sat in a wooden structure with a wooden roof that's got some pitch or something on top of it, and this sensor isn't strong enough to be able to read through that. So you really do need to be out on the open to be able to get this to work well. So if I go now for, I think is it demo 3, let's give that a go. So this is a kind of a tidier version of what we've just seen. So what this is looking for is satellites. It wants to get a satellite with all the information, so none of the commas are in there. So if we get 3 of those, we can actually get a fix on where we are. We can also get things like the time, the latitude, longitude, the speed that we are traveling in, the date, all that information we get from the satellite. So it's quite cool. You can just see there. We get the time, latitude, longitude, speed and date. Until we get 3 satellites, we can't get that, and we haven't even got 1 fixed satellite on there yet. So a bit frustrating that, but that's just, I'm inside. It does say that these don't work inside. And again, if you use your iPhone, what kind of antenna must they have in there that they can actually work inside most structures? It's pretty cool. Now it does say sometimes it takes like 5 to 10 minutes to get the satellite fixes from a kind of cold start, but I've set this running for quite a while and I've not been able to get them inside, so I'll give that a go outside at another point and film the results of that. You can see there we're getting a few more ones there, and there seems to be some errors as well. It says decode. There's a decode error, and that's basically where we're reading in parts and then we're basically saying if part 2, well, if it's only got 1 part because it only has part of the information, you get these index out of range errors. So I just need to tidy the code up a little bit on there as well. So yeah, it's pretty cool. Pretty cool that you can actually have these GPS units and they're under £20 now. There was a time where these were like hundreds of pounds. They are now very, very affordable and also very, very small. These weigh quite a lot though, the actual ceramic antennas. There's these really, really tiny ones. I'll go onto the overhead camera and show you these a bit closer up. So this is kind of the smallest one, and you can see there it says this is a Blox Neo 6M, and this other one also has the same chip. See, that's also the exact same chip. Let's get that to focus in. So Blox Neo 6M, but this one has a much larger antenna on it. So I'm guessing that the larger antennas might work better perhaps. And we could take this antenna off, swap it out on this one and see if that works any better. They are kind of interchangeable. Just want to damage this as I unplug it. A bit fiddly to do though. Do this without breaking it. Put this larger antenna on and see if that helps. It sort of clicks when it's on. There we go. Let's see if we can run our code again and get that to work. Okay, so I'm running the code again. We'll give it a couple of seconds and see if it finds any additional satellites. Like I said, it does take a little while, at least 30 seconds I think, for it to acquire them. So Laurie's saying there, I was able to add an external antenna so I could use my GPS module inside my lab. I put the end of the external antenna on my windowsill, works great, get about 9 satellites. That's pretty cool. Yeah, I was really disappointed when the first one I tried, which is this one here. Like I said, I got this from Liverpool Make Fest. There was a guy selling all kinds of parts, or almost like a sweet shop. You've got like a whole bunch of parts, LEDs and things into a little paper bag. and this one was only like $5. And I was like, ooh, GPS unit for $5. But yeah, it turned out it just goes red hot, and I think that means there's some internal short or issue with it. So I don't know. So yeah, it doesn't look like I'm acquiring any satellites inside here, so I think I'll have to do what Laurie says and put this near a windowsill or just use it outside and see if it works. But that'd be pretty cool when we actually get that data into our robot, because we can then have a fixed position. We know an absolute position where we are, and we can also use the other data from using our Madgwick. We can combine all that together to have a much better position. So the question there from Q saying, where do I get that little yellow frame? This one. So I'll put this all on the write-up once I've done a bit more work on this. So this is basically the very first video. This is like pre-1 video for this project. So once I've got the parts assembled and things are kind of working better than they are at the moment, I'll definitely publish all the files all open source. And the idea at the end of this is that we'll have a PCB that you can either buy or you can just send off yourself and get them created. It'll all be open source, and then you can assemble it all on that one board quite neatly. Cool. So that's the demo that I want to show you of the IMU and also the GPS unit as well. So if you want to join our Discord server, we've got a whole bunch of really cool people on our Discord server. You can get a free link to that going to kevsrobots.com/discord. Yeah, free sign up link for that. And if you want to follow me behind the scenes and see the kind of progress I'm making on there, I was asking people if they had any advice on building a drone, and people just said, just go for it. I'm like, I literally know nothing about this before I start, other than the kind of components I would need to make this work. So I know the parts of a drone. I have a Phantom 4 Pro, a DJI one. I've not flown it very often, but I do have one of those. That's amazing. That's great big batteries, and it has like a half an hour, there's a 35-minute flight time per battery. I've got like 3 or 4 batteries on that as well, so definitely be playing with that as I learn more about drones. So yes, if you want to follow me on there, then I'm on Threads at kevinmcaleer@threads.net. I'm on TikTok at kevinmcaleer6. I'm on Instagram at kevinmcaleer, on X at kevsmac, on Mastodon at kevsmac@mastodon.social, and I'm also on Blue Sky at kevsmac.bsky.social as well. So follow me on there, say hi, share any projects that you're working on. That'd be also amazing. And if you want to join me and support the channel, then you can do that a number of different ways. You can do a super thanks, which is I think on the YouTube page, when you click subscribe, that gets replaced by a join button, but I think there's also a thanks button on there, which is a way of sort of offline saying thank you. There's the super chat. If you're watching this live, you can do a super chat, which is just you press that $1 button there and you can do like a one-off donation. If you want to join the YouTube membership program, that's another way. So click on the join button and then you can just like make a monthly for the price of a coffee per month. Or you can do the buy me a coffee. If you don't want to be inside YouTube, you can do the buy me a coffee method, which is either a single payment or a monthly one as well. All those things are available via kevsrobots.com/coffee. And there's a bunch of people who have already done that, and I want to give a shout out to those people right now. So over here we have the buy me a coffee side. We've got Boris, who bought a coffee recently. Andrew Spencer bought 3 coffees this month. We've got anonymous member. We have Silicon Fiber, Marie TKD, Jeff Johnson, Dean Corty, Marlene Brent, and Tom. They're all members of the buy me a coffee side. And then on the YouTube side over here, we've got Brian, we have Justice, we have Pierre Eves, we have Orksrad39, Bert, Marie, Michael, Steve, Ford, Bello, Johnny, Stephen, John Paul, Cassie, Tinkering Rocks, and Johnny Bates and Tom. So yes, thank you to all those people who have supported the channel and have been doing so for quite a long time. Really means a lot to me that you continue to do that. And it's at this point in the video, if I go over here to my little, there's an unusual shot there, wasn't it? There's a little spinny logo, and that tells me that YouTube will be recommending over here a video from the backlog of videos that we have. It's picked one out just for you, so you can continue binge watching this awesome content. So definitely share this with your friends, your students, your fellow teachers or whatever, and yeah, that can really help the channel grow as well. Cool. So at this point in the video, I'll say thank you so much for watching, and I shall see you next time.